Hello, Honors Pre-Calc. Today we're going to be starting lesson 2.6, Rational Functions. In this lesson, students will algebraically and graphically distinguish between holes and vertical asymptotes for rational functions. Students will write equations, horizontal and slant asymptotes. Students will graph rational functions, and students will identify the domain and range of a rational function. What you should already know, obviously, is a polynomial function. A rational function, a word that I keep saying over here, is a fraction of polynomial functions, right? Here's an example down here in the bottom right box. You have a polynomial in the numerator and a polynomial in the denominator. And together that makes a rational function. I usually remember this just by thinking of the fact that rational almost has the word fraction in it. It's close, it's 2 letters off. So that makes me remember that it's a fraction. You can also think of a rational number, which is a fraction of integers. And then you also need to know domain and range. Our essential question today is, how do you graph and describe the features of a rational function? All right, so here are our notes, 2.6 rational functions. First of all, the official definition of a rational function is a quotient of polynomial functions where the denominator is not 0, because then we would have bigger issues. An asymptote is a curve approaching a certain line for infinity without actually touching it. We'll see some examples of that. We'll see vertical, horizontal, and slant asymptotes today, but we'll get back to that. So let's take a look at example 1. Examine a rational function. Let's just start by graphing the most basic rational function there is, 1 over x. So on my calculator, I already entered all of the functions that we're going to need today in this video so that I don't have to waste your time with me typing them in. So I'm going to graph just the first one, 1 over x. And there is a rough sketch of it. So I'm actually going to draw a rough sketch over here. And it looks something like this. All right, the parent graph here, we actually learned as the reciprocal function because 1 over x is like the reciprocal of x. It's another name for this. But the more advanced that these get, like you see in example 2, we're definitely going to only refer to those as rational functions, not reciprocal. So here, the domain is going to be almost all real numbers, but when x equals 0, if you look up and down the y-axis here, there's no point ever with an x value of 0. This curve just keeps going forever to negative infinity. This curve keeps going forever up to positive infinity. And it never touches the y-axis. So this domain is going to be negative infinity to 0, union 0 to infinity. There are vertical asymptotes here. So vertical asymptote, remember, is vertical meaning straight up and down. And like we just said, that y-axis right there, this curve is going to approach it and get closer and closer to it forever, but never actually touch it. And that's the definition of an asymptote. So that y-axis has an equation of x equals 0. Every point on the y-axis has an x value of 0. We also have a horizontal asymptote in the same way. On the x-axis, the curve will never actually touch the x-axis. It'll just approach it forever. And so that line has the equation y equals 0. Every point on the x-axis has a y value of 0. All right. In example 2, we're going to be finding the domain, the vertical asymptotes, and horizontal asymptotes of each rational function. So to do this, let's start with the domain. So for the domain, we know that in a function that is a fraction, the denominator can't be 0. And that's going to be the only reason that these functions aren't going to exist, is if the denominator equals 0. So to find the domain, what we're going to do is set the denominator equal to 0. And for this first one, we can factor. Well, there's different ways we could do this. We could add 1 and then square root both sides, or we could factor. We're going to get the same answer either way. I get x equals -1 and x equals 1. So what that means is, remember, this was the denominator. And if we plug in -1 or +1, we're going to end up dividing by 0, which is going to be a big problem. So if we want to write the domain, we'll just write interval notation excluding the -1 and the 1. So it'll look like that. The next part is the asymptotes. We want vertical and horizontal asymptotes. So I'm going to go back up here so we can take a look at what that means. The vertical asymptote, the graph of f has a vertical asymptote at the zeros of the denominator, right? But notice that this, right before we get to the idea of asymptote, this says that the function n of x and d of x have no common denominators. The numerator and the denominator can't have common factors, sorry. And so what we need to think about here is the vertical asymptote. It's the zeros of d of x as long as it is not also a zero of the numerator. So let's add that into our definition here. The graph has vertical asymptotes at the zeros of the denominator as long as it's not also a zero of the numerator. And we're going to apply that down here in letter A. So let's start with the vertical asymptotes. So I'm going to write VA to represent that. And the vertical asymptotes are when the denominator equals 0, and we found that we had an x value of -1 and an x value of +1. So now we want to check, do either of those numbers make the numerator also 0? If we plug in -1 into the numerator, we will get 2. If we plug +1 into the numerator, we'll get 2. So none of them equal 0, so we're good. So both of these are vertical asymptotes. And for horizontal asymptotes, let's go back up and look at what this tells us. We are going to be studying the degree of the numerator and the degree of the denominator. So if the numerator's degree is smaller, y equals 0 is a horizontal asymptote. If the numerator and the denominator degree are equal, then the coefficients divided by themselves is the horizontal asymptote. And if the numerator is greater, then the graph has no horizontal asymptote. This can be a little bit complicated, so we are going to learn a shortcut to remember this. And the shortcut is, how am I going to squeeze this in here? I'm going to do my best. It's Bobo Botten eats DC. I'd be curious to hear if your Algebra 2 teacher taught you this. We have Bobo Botten, so Bobo, B-O-T-N, Botten. And then the last one is eats DC. Bobo Botten is a giant, apparently, who's literally going to come and eat Washington, D.C. But this is fictional. This is not real. The idea is just to remember that phrase, and this is why. It's all about the degree of the rational function. So if the degree, so the exponent, is bigger on bottom, then the horizontal asymptote is 0. That's a 0 right there. If the degree, the exponent, is bigger on top, then there is no horizontal asymptote. And if the degree or the exponents are the same, then we divide coefficients. So that lines up exactly with these three sentences. If the degree is bigger on the bottom, the horizontal asymptote is y equals 0. If the degree is bigger on top, there is no horizontal asymptote. And if the exponents are the same, then we divide the coefficients to get the horizontal asymptote. So let's apply that down here in letter A. If we look at the degree of the numerator and the degree of the denominator, what we find is that the exponents are the same. They're both 2. So what we're going to do is divide the coefficients. So the coefficient on top is 2. The coefficient on the bottom is 1. We only care about the coefficients of those x squared terms. So we have y equals 2 over 1, which is 2. So what I'm going to do is on my graphing calculator, oh geez, well, apparently I have to charge, but hopefully that will last for the video. We'll see. If I look at the graph, what we should find is we have a vertical asymptote at -1 and 1. So you can see x equals -1 is that vertical line right there. X equals 1 is that vertical line right there. So you can see we have those asymptotes. And then horizontal at y equals 2. You can see as we go to the left and to the right, the function's approaching that horizontal asymptote. So we found all the asymptotes, everything worked out, we're good, all right? Let's try letter B. So we're gonna do the same thing. We'll start with the domain. And to start, it's usually a good idea to factor both the numerator and the denominator. So that's what I'm going to do first. On top, we're going to end up with x plus 2, x minus 1. And on the bottom, we're going to end up with what? X minus 3 and x plus 2. So we got x squared plus x minus 2, x squared minus x minus 6. Perfect, okay? So for the domain, as usual, we just check the denominator. And anytime the denominator would equal 0, we want to exclude that from our domain. So our domain is going to be -infinity to -2, -2 to 3, 3 to infinity. I missed a u there. Should be just like that. So there's our domain. Then let's check the vertical asymptotes. So remember, for the vertical asymptotes, we check the denominator, and we want to look for zeros of the denominator that don't also appear on top. And what I noticed when I factored is that we have an x plus 2 on the top and an x plus 2 on the bottom. That signifies that when I plug in -2, I'm going to end up with 0 over 0. What that does is it causes a hole in the graph, but not an asymptote. And we'll see what that looks like when we look at the graph on the calculator in a minute. But we have a hole at x equals -2. All right, so for the vertical asymptote, that's going to be the 3 because the 3 doesn't show up in the numerator. So we have 1 vertical asymptote this time. And for horizontal asymptotes, let's compare the degree of the numerator and the degree of the denominator. Once again, they're the same. So that's each DC. Exponents are the same. Divide coefficients. So 1 divided by 1. So we're going to get y equals 1. All right, let's take a look at the graph of this one. Okay, so you can see we have that vertical asymptote at x equals 3. We have a horizontal asymptote at y equals 1. We have a hole at x equals -2, and that is not actually visible with the limited pixels on your calculator screen. It just kind of skips over the fact that there's a hole there, but I bet if we go to the table, you'll see that at x equals -2, we have an error. So you can see that it's just jumping over that -2. And that's because the 0 showed up on top and on the bottom. That causes a hole, not an asymptote. All right? Great. Let's keep going. 3 more questions as part of example 3. Find all asymptotes and graph each function by plotting at least 2 points on each portion of the curve. Okay, let's try this. We now have all of the skills we need to be able to do this. So in the first one, let's just see if we can track the vertical asymptotes and the horizontal asymptotes. So for vertical asymptotes, remember we check when the denominator equals 0. That's going to happen at x equals 2. And that definitely does not show up in the numerator because the numerator is just the number 3. Then we check for horizontal asymptotes. This time the degree of the denominator is bigger. So let's think about Bobo Botten. We are bigger on the bottom, so we have an asymptote at y equals 0. So over here on our graph, I'm going to graph both of these asymptotes to get us started. So we have a vertical asymptote at x equals 2. Horizontal asymptote at y equals 0. And then what we're going to do is on the calculator, we're going to check that and then try to plot at least 2 points on each portion of the curve. And I'll show you what I mean by that. So let me go ahead and graph this. And you can already see our asymptotes look good. So when I say 2 points on each portion of the curve, what I mean is every time that we have a portion like this or this, so there's 2 quote portions here, we want to plot at least 2 points for each of those. So let's look at the table, and I'm going to look for some nice whole numbers. So I got -1, -1, and 1, -3. So there's 2 points on the first portion of the curve. That's good enough for a rough sketch. And then on the right side over here, we have 3, 3, and 5, 1. Okay, and that's all we needed. So that's very nice there. We could also write the domain if we wanted to. We have all real numbers except for 2. X equals 2, so we could do -infinity to 2, 2 to infinity, but the question didn't ask us to do that. All right, letter B, f of x equals x over x squared minus x minus 2. To start this, let's factor as much as we can. So the numerator is just going to stay x. The denominator can be split into x minus 2, x plus 1. So our vertical asymptotes this time are going to be every time that one of these factors equals 0. So we got x equals -1 and x equals 2. And neither of those x values makes the numerator 0, so we're good. For the horizontal asymptotes, let's see, what can we do here? We have, in the original, you can see that the degree of the numerator is 1 and the degree of the denominator is 2. So we're bigger on bottom. When we're bigger on bottom, we have a horizontal asymptote of y equals 0. That's Bobo. Okay, so let's graph these asymptotes. X equals -1. X equals 2. And y equals 0 is our horizontal asymptote again. And now I'm going to go back to the calculator and take a look at the graph. Cross our fingers that we have the asymptotes correct. So far, so good. Yeah, this time we have a center portion. And notice that the center portion goes through the horizontal asymptote, but that's okay because on the edges, that's still an asymptote. It doesn't have to be true for the entire graph. So that middle section isn't kind of ruining the fact that the x-axis is a horizontal asymptote. But now we have 3 sections, so we need points for all 3 sections of the curve. Let's see what we got here. Doesn't look like we have very nice numbers, so we're just going to have to make do. So -2, -1/2, and -3, -3/10. Something like that. And then we know that's curving down like this. In the middle here, we have 0, 0, and 1, -1/2. And that was doing something like this. And on the right over here, we got 3, 3/4, and 4, 2/5. So just a rough sketch looks like this, and all asymptotes are in play over here. Again, it's not a problem that we went through that horizontal asymptote right there, as long as it's an asymptote for the edges of the graph. It's more about the end behavior, right? Okay. Let's look at letter C. For letter C, if we factor, we'll end up with x times x minus 1 on top and x plus 1 on the bottom. So for vertical asymptotes, we check when the denominator equals 0. That's x equals -1. The numerator does not become 0 when we plug that in. So we're all good there. For horizontal asymptotes, we check if the degree on top or on bottom is bigger. This time the degree on top is bigger. So that's the bottom part of the bottom, right? Bottom, B-O-T-N, bigger on top, none. So we have no horizontal asymptote because the degree was bigger on top, okay? Then notice that this says check for slant asymptote. So we can sketch that vertical asymptote first at x equals -1. But there's also this thing called slant asymptotes that you might remember from Algebra 2. If we go back over here, let's read this. If the degree of the numerator is exactly 1 more than the degree of the denominator. Do we have that? Yes, the degree on top is exactly 1 more. So if that's true, the graph has a slant asymptote. To find the equation of a slant asymptote, use long division. The resulting quotient, not including the remainder, is the line that the graph approaches. Okay, let's try this. So technically, a fraction always just means division, right? So we've got x squared minus x divided by x plus 1. And we can do that as actual division. Now, it's said to use long division, but since the bottom is linear, x plus 1, it's going to be a lot easier if we just use synthetic division, and it's going to give us the same answer. So we're going to cheat and use synthetic division. And on top, we're going to be dividing x squared minus x by this -1 out here. So we have a coefficient of 1, and then a -1, and there's no constant term, so we need a 0. So we bring down the 1, 1 times -1 is -1, add down, multiply, add down. So what that means is our function, x squared minus x over x plus 1, can be rewritten because if we do this divided by this, what we get is, and we got a remainder, a constant, and an x term, so we have x minus 2 plus 2 over x plus 1. Okay, so this divided by this equals this, right? So now think about what that statement said on the front was that the result, not including the remainder, is the slant asymptote. And here's why. An asymptote that's horizontal or slant is thinking about end behavior, right? So it's like as we plug in bigger and bigger x values, so 10 or 20 or 30 or 100 or 1,000, it's all about what are we getting closer and closer to on the graph, right? So think about if we plug in bigger and bigger and bigger and bigger x values into this whole thing, this denominator is going to be getting bigger and bigger, right? If x keeps growing, this denominator is going to keep growing. A fraction with a denominator that keeps growing is going to be getting close to 0 because 2 over 5 is a lot bigger than 2 over 20, right? Think about that. The denominator growing means the fraction's getting smaller. So what that means is that as we get bigger and bigger x's, this chunk right here, the remainder is going to approach 0. Which means then we're left with this x minus 2. We're left with the rest of it to become our asymptote. So let's sketch that line. So our asymptote is y equals x minus 2. So there's our vertical asymptote. We already sketched. No horizontal asymptote, but this time we have a slant asymptote at that x minus 2. So we go to What the? Oh yeah, okay. So we have a y-intercept of -2, and then we have a slope of 1. So I'm going to sketch that line. And let's take a look at the graph to see if we are on the same page. And you can tell that we've got a portion down here and a portion up there, and you can almost see the slant asymptote is that line right there. That's this line over here. So let's plot 2 points on each portion of this curve. So there's our asymptote at -1. So we're going to plot -3, -6, and -2, -6. So we don't have much of our curve down here on our graph, but it does something like that. And then the top part goes through 0, 0, and 1, 0. And does something like this. Okay, and it approaches that dotted line. My curve kind of went over the dotted line. It approaches the dotted line. So that's a rough sketch there. All right, but that is it. That's the end of notes. So now we know how to do, we discussed domain, we discussed vertical and horizontal asymptotes, we discussed holes, and then at the end here we got slant asymptotes as well. So when you go and look at the worksheet, 2.6, you're going to first be asked to match example work with what it might be showing. Notice that when we have N and M here, it's talking about the N and the M for the horizontal asymptotes. We kind of switched over to Bobo needs DC, but you can do it by using N and M. As you're going through these, and if you look at the answer key, you're going to see that I crossed off the range for each one of these, and that's totally okay. I encourage you to cross that off since we didn't really discuss it, and it gets a little bit more complicated than we're really bargaining for. So we can just cross those off. Don't worry about that. Should have done that before I printed it out, but I didn't think of it. And let me think, is there anything else we want to go over? You just got to fill in each box with whatever you can, okay? When it says extra points, it just means plug -4 in for X and see what you get for Y. There's no trick to that. And then plot everything and check on your calculator. All right, let me know if you have questions. Thank you very much. Check your work on Schoology and have a great day.